Hello, this is Mr. Gieske. I'm going to show you what the weighted average is all about as it relates to our work in pre-calculus. Um, I think the first thing to start with is to recognize that a weighted average is really the same as a classic mean in its form. So if we start with the classic mean calculation of say 89, 77, and 93, we get 89 plus 77 plus 93 over 3. And before I compute that, I'm just going to liken that to this expression here. 89 times 1/3 plus 77 times 1/3 plus 93 times 1/3. And what this does is it shows you that each number, 89, 77, and 93, is contributing a third of itself to the sum of these three numbers. And what's worth recognizing here is that the percentage being contributed, in this case 1/3, is equal for each number, 89, 77, and 93. If we wanted to calculate a weighted average, let's say that these three numbers, 89, 77, and 93, were grades that a student got in a course, and instead of giving each component an equal weight, let's say that the course said that the 89, let's say those were tests, and that was 60% of the grade. Let's say the 77 was the homework, kind of a slacker, 15%, and then did well in the end of the course on the exam, came through with a 93, and that's the remaining 25%. Okay, the weighted average of this is going to make a lot of sense if you think about the fact that we're going to now contribute 60% of the 89, 15% of the 77, and 25% of the 93. We get something that looks a lot like the red expression above. It's going to be 89 times 0.6 plus 77 times 0.15 plus 93 times 0.25. Okay, now we've given them different weights. I'll put a 0 in here just to show that it's clear, the percentages. And now you can see that the 89 is going to dominate, as it should, and the 93 is going to come in pretty heavy, and the 77 is going to come in least contributive. So in this sense, you can see that the classic mean is in fact a weighted average. It's just that you give the same percentage to each component. Let me just hit pause. Okay, so I'm going to compute these two numbers now. My little calculator here. We're going to do 89. I'm not sure why this is. Okay, 89 plus 77 plus 93. You guys may hit enter at this point. I like to do it all in one expression, so I'm going to insert some parentheses back here. Divide by 3. Okay, this number comes out to be 86 1/3. Okay, and in blue, we've got 89 times 0.6 plus 77 times 0.15 plus 93 times 0.25, and that comes out to be 88.2. As we'd expect, the weight of the 89 carries the average a little higher. This is an equal to 88.2. Okay, now the reason why I calculated these numbers is to show you a metaphor for explaining these numbers. A weighted average can be also thought of as like kids sitting on a seesaw. So the red average, actually I'm going to do a little of this, pull this down here. Okay, the red calculation, if I were to balance these guys on a seesaw, I would take the relative positions of 77, 89, and 93, and I would put equal weights. For example, it doesn't matter that they have the size 1/3, they just need to be equal in size. So I'm going to put a box there as to indicate that there's a weight sitting there at that position. A box here and a box at 93, and they're all the same weight. And what this 86.3 is the fulcrum upon which the seesaw would balance. Okay, that's the way you think about the mean. And this should make sense to you intuitively. You've ridden on seesaws before, and if you're riding with your little sister or something, and she's half your weight, and if she sits twice as far away from the fulcrum as you do, then it'll balance. The same idea is at work here. It's just that it's a little more complicated with 3 items, and the relative positions have to correlate with the relative weights in there and make the fulcrum the mean. So the blue one works the same way. It's just that I'm going to put different size weights on each spot. So if I draw the same seesaw, 77, 89, and 93, but I have to put different size boxes on. So I've got the numbers here. They're not perfect to see, but if I put a 0.6 box here, and I put this is going to be a quarter the size. 0.15 is a quarter of 0.6. And then 0.25 is a bit bigger than that. Not quite half. Okay. Except I put them in the wrong place. Whoops. Let's try that again. '77 has the quarter size. The 89 has the tallest. And this is not quite half. Okay, now if I balance these blocks on a seesaw, the mean pushes up a little higher to 88.2. It's not the mean, sorry, the weighted average. Okay, now we still call it the mean, but in this case, I think it's more clear if I call it the weighted average. So I think that should make sense to you. There's 2 things to take away. One, that the classic mean is a weighted average. It's just that all the weights are the same. And 2, that the weighted average computation is a multiplication of the value times its weight. And you can see that the metaphor for the seesaw indicates that you've got positions as the test scores and the boxes on top of the seesaw as the weights. And I think that that metaphor will carry forward. Okay, I hope that's clear.